Hello, my name is Gary Millett. I'm going to be your guide through this presentation. It's fairly long. It's topic number 2, Introduction to the Internet of Things, Cyber Physical Systems. So let's get to it. So the title of this slide is Introduction to the Internet of Things and Cyber Physical System Technology. So what we have here is a focus of the presentation. We want to provide an overview of what's known as cyber physical systems, which we have an acronym of CPS for, cyber physical system technology, and its relationship to the Internet of Things, or IoT. So the goal of this module is to introduce the reader to these emerging technologies by examining the evolution of the Internet and the various underpinning technologies that are enabling the next generation of Internet applications. The Internet of Things and their subsequent enabling of cyber physical control systems. We'll have numerous examples of, some systems that people have proposed and people are working on. But let's first consider some definitions. What are smart systems? Well, everyone's familiar with the present-day microwave oven that has built-in ability to control its operation via inputs through a keypad. And in this simple case, the microwave oven has built-in embedded control. That's in the form of a pre-programmed microcontroller. This microcontroller is an inexpensive computer-like electronic device that can run a stored program that performs the required functions of the device it is embedded in. Microcontrollers have been around almost as long as microprocessors. It turns out that many more microcontrollers are sold than microprocessors are. And it turns out we've gone to 4-bit to 8-bit to 16 to 32-bit microcontrollers at this point in time, and they're very inexpensive. Let's get back to our microwave oven. When you place a bag of microwave popcorn in the microwave oven and you press the key labeled popcorn, the embedded controller accesses a subroutine that activates the microwave power source and controls the duration of its operation and oven power output until the popping process is close to completion. This is usually detected by a humidity or moisture sensor. Most modern microwaves at that point then go into a standard number of seconds that they'll keep the power on before the process is complete. Another example of this type of application is the automatic electronic fuel injection, or EFI system, of a modern gas-powered or hybrid automobile. Anything that has a, run by gas. When one starts their automobile, the EMC, which is the electronic control module, starts to implement a program that automatically supplies an optimum mixture of gas and air to the cylinders and a controlled spark to ignite the mixture, thus efficiently providing power to propel the automobile even as driving conditions change. We should point out that the ECM is constantly receiving a large amount of under-the-hood sensor data that goes into the determination of the optimum gas and air mixture as detected by the O2 or oxygen sensor located at the engine's exhaust manifold. The next slide shows some additional detail about the smart fuel injection system used by all modern automobiles. Note all the various sensors used by this system, the ECM, and the OBD2 interface for troubleshooting if a problem arises. So here's this diagram. By the way, there's a link to a YouTube video that's pretty good about EFI down the bottom there. So on the left-hand side, critical EFI sensors, air intake, throttle, timing, and emissions. A mass airflow sensor, a MAF. Manifold absolute pressure sensor, a MAP. Throttle position sensors, no longer the gas pedal, TPS. EGR valve position sensor, and cam position sensor. You may have encountered one of these devices going bad in your car and have to have it replaced. This is a modern, again, electronically controlled car. Notice the sensor bus, all the dotted lines from the sensors. On the right-hand side of the sensor bus, a barometric pressure sensor, engine coolant temperature sensor, air temperature sensor down below, NOx sensor, vehicle speed sensor, and the heart of all that is an electronic control module, an ECM. Notice it gets DC power, 10 to 14 volts from the battery and the the voltage system of the car. Puts out sensor power of 5 volts to the sensors. There's an output that goes to OBD2 interface. The OBD2 is onboard diagnostic system 2. There are ignition signals that go out to the ignition system on the right-hand side, and there are injector pulses that go out to the fuel injectors. So the pressurized fuel comes from the fuel pump, which is usually in the gas tank today. And this is a 4-cylinder car, so we got 4 combustion chambers. So injector pulses, we got 4 injectors there. Chamber number 1 in the top through chamber number 4 in the bottom. Atomized fuel goes into the chambers. The spark from the ignition system down the bottom goes into the chambers at the same time to the spark plugs. The combination of the fuel and the air is ignited, and in the process we have an exhaust cycle where the gas goes out to the exhaust catalytic converter. At this point there is 2 purposes to the catalytic converter. One is to scrub the exhaust of pollutants, plus there are oxygen sensors. They can be fore and after the catalytic converter, and eventually the exhaust goes to the muffler. Those oxygen sensors, as you notice, the dotted line goes all the way back to the sensor bus, and that's where we're looking for the correct combination of fuel and timing to have the correct output from the oxygen sensors. So today, most products that use electricity to power their operation tend to be designed with varying amounts of embedded control to increase their efficiency and functionality. In fact, a modern automobile can have upwards of 50 to 100 microcontrollers, we call them ECUs in that industry, to assist in its operation. Now, this translates into the average amount of electronics in a new car being equal to about 1/3 the entire cost of the car. That's quite impressive. Although we get to the next couple things here. Most predictions are the percentage of the entire car costs that are attributable to the onboard electronics and software will keep on increasing. This will be even more evident as we transition to hybrid and electric vehicles. If one does a search on Google or YouTube, there are many examples of the use of electronics in automotive applications. And some have called today's vehicles supercomputers on wheels. I mean, the processing power, all these little microcontrollers and so forth, is much more than the initial computers that were first invented way back in the 1940s. An extension of the smart system concept to our physical infrastructure results in what we call intelligent or smart infrastructure systems. Of course, what we mean by infrastructure is open and wide definition. Typically, politicians would define infrastructure as our roads and bridges, but in reality, it's all the structures found in a civilized society. This long-time definition might be changing in 2021 to include things like healthcare and other social safety net programs. Time will tell. I believe today, actually, as I record this, the Senate voted to accept a bipartisan infrastructure bill that deals with the things I mentioned in the second bullet here, roads and bridges and actually internet access and things of that nature. Physical things. So if we limit ourselves to the more traditional definition, smart infrastructure is an edifice that has embedded sensors and utilizes modern data communications technology to transmit or relay the sensor data to some monitoring or control point. Today, there may or may not be embedded control present in the infrastructure depending upon the type of infrastructure. A bridge might not have embedded control, whereas a building might very well utilize embedded control to optimize its efficiency. When considering infrastructure such as roads, bridges, or buildings, the civil engineering community likes to talk about the health of the structure. The health of the bridge, the health of the road, the health of the building. Accessing a structure's well-being can be facilitated by using the intelligence sensors built into the structure to monitor the stability and or aging of the structure. There are many examples of this type of application for large structures, such as bridges and sports arenas. Where they cost millions of dollars to build, we tend to put a lot of sensors into them. Here's a picture that you may be familiar with. The title is, "Could this disaster have been avoided?" This is Surfside, the collapsed condo in Florida. So today's building codes for structures like this one in Florida call for human inspections every 40 years. Could this tragedy have been avoided? Unfortunately, the type of sensor technology needed was lacking at the time it was built, and it'd be very difficult to retrofit it with the correct technology. Many other applications of intelligent/smart infrastructure are envisioned for the near future. However, these systems will take the technology a step further by using the internet to add communications to the built-in intelligence. Popular applications include things like EV charging, renewable energy resources, smart cities, smart buildings, smart homes, smart agriculture, smart transportation systems, and by that we mean automotive, rail, sea, and air, smart manufacturing, and many others, including those that enable e-healthcare applications or what we might call smart health. In other words, anything that has to do with humankind's activities and endeavors. Whether it involves interaction with the environment or with each other, these pursuits can be made more efficient, safe, reliable, and secure through the implementation of intelligent/smart infrastructure. That almost brings us to the topic of cyber-physical systems technology. Shortly, we will discuss in what ways these systems are different from smart infrastructure. But before we tackle the concept of cyber-physical systems, let's fill in some of the blanks by talking about the Internet of Things, or IoT. Now, the IoT is a concept of having just about everything connected to the Internet. There were numerous projections that there will be anywhere from 30 to 50 billion devices connected to the Internet by the year 2020. Most of these projections were more hype than fact. A more realistic view. So here's from my friends at IoT Analytics, total number of device connections. So this little slide shows again, starting on 2010, that there were 8.8 billion devices connected to the Internet. 8 billion of them were the common things like mobile phones, tablets, PCs, laptops, and so forth, where 0.8 of a billion, or 800 million, were IoT. That's the red block. So notice that this forecast from 2020 indicates that the number of IoT devices equaled non-IoT devices by 2019. So if you go to the 2019 year, you see 10 billion of each, non-IoT and IoT. So this is a start of a new data paradigm where M2M traffic starts to exceed human application traffic over the Internet. This one shows how they will be connected. So here again we have, and this is Q2 of 2020, this graphic indicates how these IoT devices will be connected to the Internet. And you might notice that, again, we have various colors to indicate what the technology is. The bottom, deepest red is wireless personal area networks, or wireless PANs. The next up above is wireless local area networks, or wireless LANs. Then cellular 2G, 3G, 4G is the pinkish one. LPWA is a very light pink. Wired is the blue. Other is the gray. 5G is the dark gray. And the light gray is wireless metropolitan area networks. Or maybe those were like blues, I'm not too sure. And again, you see the growth here, 29% growth from 2015 to 2019, and they have A's after those years, whereas starting in 2020, it's an F for forecast, all the way up to 2025. So wireless will be the way that they can connect these things to the Internet. So what are the Internet of Things devices? Well, in other words, instead of just having desktop PCs, smartphones, tablets, and web servers connected to the Internet, devices that need to be controlled or devices that act as sensors and or actuators will also be connected. We like to talk about these devices being machines. Simple machines possibly, but machines nevertheless. Hence, machine-to-machine or M2M communications over the Internet results. And again, I've already talked about this, will mark an interesting transformation as Internet traffic will become dominated by messages not intended for humans. Some of you may remember the premise of Skynet in the Terminator, one of Arnold Schwarzenegger's first movies in that series about what happens in the future. So many have contemplated this proposition and what it will mean to the internet infrastructure as time goes on. And well on its way to be fully implemented, 5G, the fifth generation of cellular technology, is gearing up to facilitate M2M traffic, and extensions to this new standard are being finalized for IoT applications. They're supposed to happen this year and next year. IP version 6, the newest IP addressing scheme, has more than enough addresses. IP version 4 is out of addresses at this time to accommodate the anticipated need for device addresses as we enter the IoT era. So even if we have 1 trillion IoT devices, it turns out IP version 6 will take care of that. Facilitated by emerging wireless technologies, this new era of the internet is but one more enabler of new digital applications like cyber-physical systems. So as will be mentioned shortly, some cyber-physical systems need extremely low latency to be able to function as intended. Now, these types of characteristics have already been initially added into wireless communication systems like 5G, as well as existing telecommunications protocols. So what is a cyber-physical system, or what is cyber-physical system technology? Certainly a good starting point would be to define what we mean by cyber-physical system, or what is a cyber-physical system. Another question to answer is, what are the enabling technologies that are allowing cyber-physical systems to come into existence? Answering the last question first, cyber-physical systems are made possible by sophisticated sensor systems and the availability of our pervasive internet infrastructure. This is further enabled by today's wireless technologies that provide for mobility. So what are cyber-physical systems? They are embedded control systems that are tightly coupled to the real world and require proper timing to perform their function. That is, the ability of the system to be tightly coupled is provided by sensor systems that are connected to the embedded control systems locally or through the internet. Timing is the critical characteristic that defines these systems as cyber-physical, since they operate in real time. That is, if they're controlling something, they have to be able to control it in real time. The system timing is typically provided by data communications. Usually that's over a low latency internet connection, typically 1 millisecond to less than 10 milliseconds. And people talked about some applications that will need faster times than this or lower latency. Unfortunately, this type of latency is not as yet available on a wide-scale basis and is therefore, at this point, an impediment to the implementation of some proposed systems. More about this problem and solutions, you should think 5G, as we examine applications for cyber-physical systems. So, let's take a look at some of these things people have proposed. Many cyber-physical systems are characterized as large in scope. That's both geographically and in sheer complexity. Hence, they are large-scale systems. Some examples of cyber-physical systems would be those mentioned earlier. A smart grid, that's certainly a wide in scope type of operation. In-home e-healthcare applications, smart buildings, again a large thing. And transportation systems, that is smart cars, autonomous cars, and so forth. And so traffic control would be a large-scale cyber-physical system. These are all control applications that require embedded controllers and critical timing to operate. So a question might be, is a modern automobile a cyber-physical system? Technically, the modern automobile qualifies as a cyber-physical system since it has embedded control that is tightly coupled locally and also has critical timing associated with it. You might refer back to slide number 7 about the electronic fuel injection. That works in real time. Some would likely be surprised to discover that the vast majority of automobiles manufactured today have multiple in-car data networks to facilitate their operation. That is, there are legacy automotive networks like CAN, C-A-N, Control Area Network, FlexRay, LIN, MOST, CENT, and more recently, Automotive Ethernet. And all indications are for an increasing use of new two-wire Ethernet technology in the future, with the added feature of the availability of connections to the internet. That was started by Elon Musk with the Teslas. Even though the modern automobile is technically a cyber-physical system, It's limited in the fact that cyber-physical system technology is vehicle-centric. This vehicle-centric framework only provides limited information about the surrounding environment. Until recently, for the typical current automotive CPS configuration, most safety-critical sensing is aimed at minimizing the severity of any accidents, not preventing them. A passive approach to accidents, but an active approach to preventing or diminishing passenger injury. Now, this limitation can be reduced by knowing where surrounding vehicles are located and what they are doing. Many of this is the holy grail of autonomous driving. Many of today's vehicles come equipped with sensors, things like radars, ultrasonic sensors, cameras, and so forth, that provide this type of information with a future goal of improvement with the addition of sensors like LiDAR. So we're looking around us, that's for sure. However, the best solution would be for neighboring vehicles and/or surrounding infrastructure to share information about their proximities and status in cyberspace. This sharing of both location and vehicle status, things like location, speed, and direction, coupled with information about braking, hard braking, lane changing, turning, acceleration, past travel, and so forth. You share this information through cyberspace. Can best be accomplished by connecting or communicating these parameters wirelessly from vehicle to vehicle. The acronym there is V2V. We should make note of the importance of the timeliness of the information provided to the automobile CPS if it is to be of any use in collision avoidance. Recall the importance of latency or time delay to the cyber-physical system. Recently, the term smart or context-aware cyber-physical systems have been used or has been used to differentiate between local-centric CPS or a CPS system aware of its environment. Smart or context-aware CPSs are those that are aware of their environment and react to it. Some would or might call this a form of cognition, or maybe AI, artificial intelligence. This technology started out as locally embedded systems. You might recall our microwave oven, evolved to networked embedded systems, and will eventually evolve to cyber-physical systems or smart everywhere. Now, there are many YouTube videos devoted to cyber-physical systems. This following one is about 10 minutes long and fairly informative. I looked at many of them, and this one is, again, the length is good and the information is good. It's less than a year old, I believe, also. So what's a general model of a cyber-physical system? So the next slide shows a simplified generalized block diagram of a cyber-physical system. The block diagram shows that several processing platforms are used, many sensors are used, and a networking fabric is necessary for the correct operation of the system. The physical system is interfaced to the sensors and actuators of the control system in a classic closed-loop system. Got an asterisk there. I think that means you want to go to topic number 3 if you're not familiar with classic closed-loop control systems. It also has critical timing invoked by the system. Now, this diagram I came up with, excuse me, so it's not the best one, and this was before there were any other diagrams. There are several books out there now that have different diagrams. So you see here platform 1, platform 2, platform 3. Those are different computing platforms. In platform 2, there's one sensor and a computation. Platform 1, there's 2 sensors and some computation. The term data fusion might be used for that. Over in platform 3, you notice that computation C and computation D and computation E, some of that is fed back through the network infrastructure, which might be wired or wireless. There's also a sensor number 4 and platform number 3. And the physical system is down below. That's what's to be controlled. And then from the far right platform 3, there's a merge or fusion. Might be data fusion. Actuator A, physical interface to the physical system to control it. So again, this is something I came up with. It's certainly not the best in the world, and I'm sure different block diagrams will evolve as time goes on, and When I find a better one, I'll use that instead of this. Here's one that I did find, and this one is it depicts the integration of physical devices, that is real physical things and systems, and virtual computational components. So this is kind of a layer type thing. It says cyber physical systems, integration of physical devices and virtual components, as a description at the very top there. Down at the Internet of Things, worldwide connectivity of physical devices in the very bottom. You see routers, you see devices are connected through routers to another router, which brings them up. We have physical device, physical device, physical device there on some type of network, local scenario of the physical world. So the second big cloud is just a repeat of what the lower two clouds are, apparently, and it turns out that what happens, we have information flow from those physical devices to virtual components, and that's a cloud that's up in the very high part of this diagram, computational world, cloud servers and so forth. And notice the information flow, the abstraction process is that we flow information up to the virtual components and it gets passed back down to the physical devices. So here the purple ring shows the virtual component being linked to the physical device on the far left of that diagram. So the connection between the real and the virtual allows for things like machine learning, we call ML, artificial intelligence basically, to be applied to the control of some real application. So note the role of the internet and how connecting to the computational world with the physical world allows for the abstraction of information from this connection. And again, when you have lots of data, it turns out you can extract information from that data. So that's that abstraction process. So what are the underpinning technologies of cyber-physical systems? Well, one might ask how we've arrived at this juncture in time. So let's digress a little bit by looking at the evolution and convergence of technologies that are enabling cyber-physical systems. We'll focus on the evolution of silicon technology or microelectronics, computer networking, and the internet, emerging wireless technology, and sensor network technology. So this diagram, I need to update it. I'm stuck in 2020 there. COVID must have stopped me from going and adding the next decade. You might recognize this as a depiction of Moore's Law. Starts way back about 1971 with the first Intel microprocessor and runs this for 5 decades here, right now to 2020, but that's last year's news. On the left-hand side, you see the number of transistors on a chip starting down there at 100, going up to 1 trillion, the very top. So we're up at the 100 billion. We're past the 100 billion at this point in time. This is the total number of transistors on a microprocessor chip versus year of production. So actually, in memory terms, for flash memory, we have exceeded that a long time ago. So over time, as could be predicted from Moore's Law, electronic systems have evolved from a collection of boards crammed full of components to systems on a board to systems on a chip, which the acronym there is SoC. Today we routinely produce ICs that contain hundreds of billions of transistors. This fact, coupled with microelectromechanical systems, or MEMS technology, allows us to build complex, highly functional systems on chips with on-chip high-powered processing cores. So here's a couple of pictures. The far left is a typical board from years ago. Might be a memory board with a lot of chips on it. And then to the right you have a Core i7 from Intel, which you might call a modern system on a chip. So Moore's Law has changed the playing field, obviously. For most electronics-based systems, the word smart has been added as an adjective to describe the system's operation. These systems are no longer fixed in what they can do. Instead, under program control, they may alter their operation in reaction to system inputs or other possible conditions that might occur. Some have predicted that future electronic systems will have the ability to evolve. And recently we have started to talk about machine learning, a form of AI. So today, smartphones have the processing power of a computer that used to cost close to $1 million. Use many kilowatts of power, required a data processing staff to operate, used punch cards or paper tape to operate, and filled a large room in a bygone era. In one of my other presentations in this series, I did mention that you can buy a Samsung, I think it's an S21 smartphone today that has 256 gigabytes of onboard memory. It pales in comparison to a trash Radio Shack 4K machine that had 4,000 memory locations. But anyway, today's microcontrollers have become extremely powerful in their computational abilities, are inexpensive, and are self-contained. As mentioned previously, embedded controllers are today routinely introduced into formerly dumb products, making them smart. Furthermore, most electronic systems are so complex today that they are not easily repairable and are dependent upon software as much as hardware for their operation. Today, we have all had the experience of having some piece of consumer electronics die on us, only to be told that it is less expensive to replace it than fix it. Of course, the added bonus is that the new model is better than the old one, typically more functionality. Today, the PC is ubiquitous, with other form factors like laptops, tablets, and smart devices like iPhones actually having the largest market share. The PC being the biggest share, or having the largest share, has long since passed by. The internet is also becoming more and more ubiquitous, and data transmission rates are becoming faster and faster. If you've got cable TV, cable modems, it turns out 200 megabits per second is more or less a standard at this point in time. And of course, you can get upwards of a gigabit per second if you so desire. Wired and newer wireless technologies give rise to the ability to communicate and or send data untethered anywhere at any time over the web or by cell phone. Today we have had 4G technology or cellular for the better part of a decade, and now we're watching the rapid implementation of the newer 5G cellular technology. You can't miss it if you watch network television today, all the commercials. The development of 5G cellular technology was put on the fast track, much like what had been done with 4G before it. So during the 2010s, the goal of implementation by the early 2020s was a target. We are now there. 3G and 4G were driven by demand for mobile data services over the internet. 5G is different. 5G technology is driven by diverse communications requirements. You could read that as M-to-M needs, machine-to-machine needs, not bandwidth. Although in some areas of the world that will remain an important driver. There are predictions that during the 2020s, there will be over 50 billion devices connected to the internet. Our IoT analytics figures showed over 30 billion by 2025. In the future, who knows? Maybe a trillion. As mentioned before, in this new paradigm, most internet traffic will eventually become M-to-M. So this little picture here shows machine-to-machine communications. Shows typical test equipment that can be controlled remotely and have measurement data accessed over the internet connection. This type of M-to-M communications is suitable for human viewing due to the type of HMI interfaces provided by the test equipment and the software used. In my lab at Springfield Technical Community College, I have a lot of not these particular equipment that you see here. This is the newest models, but I have a lot of equipment that allows for this using what's called bench view, and it turns out the students can access the readings on, say, a digital multimeter or the display on an oscilloscope using their smartphones. So what about emerging IEEE wireless technologies? Well, the IEEE wireless technologies, that is 802.11, 802.15, and 802.16, just keep evolving. First, IEEE 802.11, or Wi-Fi, is the technology standard of local area networks, which are called LANs, and has been extended by 802.11p to include vehicle-to-vehicle, or B2B, communications for automobile safety applications. Now, that's been a standard for the last 20 years. Whether it actually gets implemented is a heck of a good question. Data speeds greater than 1 gigabit per second, WiGig we call it, have been standardized for IEEE 802.11ac, and 802.11ad. Next up is Wi-Fi 6.0. We've gone to generations of Wi-Fi now, copying the cellular people. That's 802.11ax, and the use of spectrum in the 6 gigahertz band is next on tap for Wi-Fi 6.0. 802.11ac can provide data speeds approaching 7 gigabits per second in the 5.8 gigahertz band. The IEEE 802.11ad standard allows for data speeds up to 7 gigabits per second over short distances using the 57 gigahertz to 64 gigahertz frequency range. However, those are not commercially available yet. About 4 years ago at the CES show in Las Vegas, I saw a demonstration. A laptop had been, say, jury-rigged to take and do this, but you won't see any of these on the, commercially for sale yet. That technology, that high-frequency technology, is very expensive at the present time. I'm sure it'll get less expensive as things go into mass production. The FCC has authorized use of the 70 to 80 to 90 gigahertz bands for point-to-point and point-to-multipoint data transmission, much like WiMAX technology is used. The FCC continues working on opening up the 3.5 gigahertz frequency band for Wi-Fi use. Both 802.15, which we call Zigbee, and 802.16 WiMAX are considered big players in the smart grid arena. Comment about WiMAX. WiMAX kind of got a real blow back about 4 or 5 years ago now when it was discontinued by Sprint. But still, it's a big player in the smart grid arena for backhaul. And it'll probably be a niche player for other things. There's another version of 802.15 being used for body area networks, which we call bands, for medical device applications. A lot of activity in that area right now. Other IEEE standards will offer wireless regional area networks, call those WRAN. So sensor actuator technology is now available for many new areas through emerging technologies like MEMS, microelectromechanical systems, photonics, microfluidics, biosensors, and so forth. Typically, a sensor network is a deployment of an assemblage of complex sensors and possibly advanced actuators with embedded or ambient intelligence. In a wireless sensor network, sensors and actuators are linked together with modern data transport and networking technologies. What is the potential of the sensor network technology? Well, these sensor networks, combined with application-enabling software, give rise to new and potentially quality-of-life-changing applications. For many already existing situations, they have the ability to increase system efficiency, safety, reliability, and security. Applications have already been mentioned. Building efficiency, power generation and delivery, call that the smart grid, or you might talk about alternative energy sources, transportation safety, and health delivery systems. With a few exceptions, the deployment of these systems has been limited at best at this point in time. The roadblocks are primarily financial in nature, especially if one considers a geographically dispersed system. An exception is the automobile, where the economic barrier of geographically large networks does not come into play. At this time, in-vehicle sensor networks are used extensively to reduce emissions and improve fuel efficiency. Today, several factors have combined to give this emerging technology a boost. Advances in wireless mesh technologies. Mesh technologies, by the way, is where you relay signals through other nodes, other wireless nodes. Short-range wireless networking, and the continued deployment of fixed and wireless broadband technologies by major telecommunications service providers has brought us extremely close to ubiquitous high-speed internet access in populated areas. I mentioned previously, with a new infrastructure bill that is in the process of being passed by the United States Congress as we sit here on August 9th in year 2021, it turns out that there's parts of that that are set to provide funding for broadband in more rural areas. So we talk about high-speed internet access in populated areas that may evolve to all over the place. A new government infrastructure spending bill, which I put this in, I guess, will provide more deployment of high-speed internet access in rural areas. I was ad-libbing. I didn't realize I had that bullet down below. Sorry. So applications for CPS. Let's change our gears a little bit. Let's turn our attention back to the IoT and CPS technology and ask, what are the big applications? So let's just stop for a second. We've seen that cyber-physical systems are time-dependent. They control things in real time. Well, let's take a look. For quite some time now, newly designed electronic systems for complex control and monitoring and our measurement have been increasingly adopted by other non-electronics-based technologies. For instance, building sensor systems, the automobile industry, medical device industry, and so forth. Certainly in the early years of the last decade, that is the 2010s, the greatest amount of popular press was devoted to this particular application, and that was the smart grid. It was going to be the next best thing. Many in the power industry have termed this the biggest event to impact the electrical distribution and generation aspects of that industry in the last 100 years, during which time the generation, delivery, and consumption of electricity has remained fundamentally unchanged. So here's a lesson in technology that, sounds super good, win-win situation, a great deal of hype, but what really actually happened? Well, let's take a look. Before we do that, we'll talk about what it is. In theory, the smart grid is basically a service platform that will help to reduce energy consumption and greenhouse gas emissions. Again, a win-win. This platform will drive optimization, improve utilization and efficiencies, and enhance the reliability of the nation's transmission and distribution infrastructure. A win-win. Basically, the smart grid is an extremely large sensor network. At the simplest level, a smart electric meter can be installed that allows for the gathering of data and/or the disconnection of service at the meter, known as AMI, Advanced Meter Infrastructure. At a much higher level, a smart meter with communication links to the consumer and various energy-consuming devices in the residence, in conjunction with energy management software tools, can allow the consumer to control their energy usage and ultimately their cost. Somewhere in between these two scenarios is the electric power supplier remotely controlling the thermostat and energy-consuming devices in the residence. People did not like that idea. Other smart grid functions that deal with the distribution system and alternative energy sources like solar, wind, so forth, and/or energy storage systems, batteries, flywheels, supercapacitors, are termed distribution grid-facing functions by the power industry, and the smart grid would be involved with all that. Included in this class of functions is remote monitoring and control of the distribution grid and anything connected or interfaced to it. There's a term microgrid that, again, the smart grid will allow microgrids to be interfaced to the larger grid. It will take many years before experience with the system will be translated into turnkey applications. This technology is predicted to save between 10 and 15% of the energy presently being used when it gets implemented. Unfortunately, deployment of smart grid technology has been extremely slow for various reasons. So here's a little slide that shows demand response saving. Unfortunately, this is a 12-year-old chart. Shows predictions of power savings through the use of demand response programs enabled by smart grid infrastructure. And you see there the colors are 2010, 2020, and 2030. And this came from the Electric Power Research Institute in January of 2009. So if you take a look at the potential savings here, it turns out that, in 2010, a year after this chart came out, there wasn't a great deal. But by 2020, there's quite a bit. That blue gets quite large, and by 2030, even better. It turns out the smart grid received a great deal of hype when it was first conceived. One of the biggest problems is there's not really a good business model for this. Who makes money off of this, or where does the money go? How does it flow? Well, it doesn't flow to the electric power industry, so again, all of a sudden the big hype, a win-win and so forth, and it turns out that, whoa, let's slow down. Let's take this at a much slower pace and see what's going to happen. So the prediction of smart grid spending that originally happened has been delayed, and it turns out that here's another, this is a report that I believe came out in 2018, and it shows a scenario of 10 years here from 2014 to 2024, and shows an increasing willingness to invest in a smart grid as we head towards the middle of this decade. So you might notice that the pure smart grid devices systems, the spending there looks like it goes up, quite a bit. That middle bar. Some of the other spending seems to remain, fairly steady. Smart grid related operations IT seems to go up. Smart grid related administration costs tend to go up a little bit. But the spending on the smart grid hardware finally looks like it's about ready to take off. Again, the problem here is that there's no business model. Oh, another thing is I mentioned those AMI meters, the smart grid meters. It turned out in California when they installed these, it turned out people's electric bills tended to go up. That was not a good consequence. So how's the smart grid implemented? To implement the smart grid requires that a two-way communication system be overlaid on the electric grid. The network must have the capacity to enable advanced metering, home energy automation and management, distribution automation and management, and distribution generation and energy storage. Furthermore, a home area network, or HAN, and automation technology are needed to enable the consumer-facing applications. That would be, your refrigerator, your oven, things of that nature, hot water heater. So here's a diagram of a smart grid architecture, and people like to put these things in layers again. So that's kind of the influence of IT on this. At the top, you see the application layer, energy management system control, utility data center. You see a fiber optic backbone there. Communications layer, you see a WAN. You see BAN over on the top far right, a BAN. What type of network? The building area network. A HAN, home area network. An IAN is a industry area network. So it turns out that then you have the power system layer on the bottom left there, where the power generation, the power transmission. You see some microgrids, power distribution, a HAN gateway. So again, this is all very much, and then there's a 4G, WiMAX, 5G, a NAN, neighborhood area network. A lot of networking, wireless networking to implement the smart grid architecture. It's coming, but it's certainly slowed down compared to the hype that met it way back in about 2010. So from that ResearchGate model on the prior slide, you can see the various networking technologies that are needed to implement the smart grid: WANs, wide area networks; LANs, local area networks; home area networks are HANs; building area networks are BANs; industrial area networks are IANs; field area networks, FANs; neighborhood area networks, NANs, and other industry-specific networks. So you get a lot more acronyms. So implementations of these networks use many different physical layer technologies. Might use WiMAX, Wi-Fi, and Zigbee. Those are all IEEE wireless technology standards. Z-Wave is an open wireless standard. Insteon, a home automation standard. Waveness, an open wireless M2M standard. 6-low PAN, which is IP version 6 over low power wireless personal area networks, which is a PAN. Cellular, BPL, broadband over power line. Ethernet, which is again a wireline technology. LoRa, and fiber optic technology. You can do an internet search in these technologies to learn more about them. I will be talking about them in the part of the course when we talk about wireless. So what about hybrid electric vehicles and electric vehicles? So the future of electric vehicles is tightly coupled to the re-engineering of the electric grid. I think the president of the country recently talked about selling 50% electric vehicles for the year 2030. By that time, you better have a lot of electric charging stations. So it turns out, the electric grid needs to be upgraded for that to occur. You cannot, right now, the way the power grid is, if everyone had an electric car, we could not all plug them in at the same time. So that's a problem. The smart grid will allow support for demand for energy that will be generated by this new technology, that is electric vehicles, on a 24-hour basis, not just during off-peak hours. Some have suggested that a nationwide fleet of electric vehicles can be used as an energy storage system. Power can be stored and later returned to the grid. We call that V2 grid or V2G. This past week I saw a new Ford TV ad. Indicates that a planned electric truck model, I think it's the Ford Lightning they call it, can supply power to one's house. I saw that commercial for the first time, I think, during watching the Olympics. So another application would be infrastructure health. Types of sensor networks could increase public safety and possibly increase infrastructure lifespan. We talked about the Surfside condo collapse earlier. You might recall the bridge between Minnesota and Wisconsin on I-35W that collapsed in 2007. It was rebuilt with over 323 embedded sensors. Smart bridge technology. And here's a link to the St. Anthony Falls Bridge, which talks about that. Most large construction projects are using smart sensor network technology. It remains to be seen whether with this new infrastructure spending bill we have a big surge in putting sensors into infrastructure. So the smart grid is but one of many large initiatives involving sensor networks that will be implemented in coming years. So although not discussed in any detail yet, building and home automation have already been mentioned as technologies that, coupled with sensor networks, could most certainly provide increased energy efficiency and increased safety and security. You might consider how much energy is wasted by out-of-date heating systems. Here's a cover of Time magazine, Smarter Home. So this kind of indicates the new technologies in the public's eye and that various products are being put in the marketplace to fulfill this dream. I have a link there which looks at smart home products that were introduced at the CES show in 2020. Future applications, we switch gears a little bit to e-healthcare. So e-healthcare initiatives in the home healthcare arena for an aging population are on the radar screens of many researchers and the healthcare industry. There's a link there. You might want to take a look at that little video from YouTube. And recent journal that I subscribe to, dedicated to wireless e-healthcare topics, included articles on ECG monitoring through body area networks, second generation or 2G RFID-based systems, human gait tracking, emergency response, early detection of Alzheimer's disease, telemedicine, and so forth. And there's another YouTube video you might want to take a look there also. One may ask, how are these applications possible? Basically through a combination or fusion of remote sensing data and sophisticated software applications. For instance, gait tracking compares an individual's normal walking gait versus any changes to the gait. You can learn lots of things about what's going on with that person. Recently, researchers have shown that low-power radar systems can determine a person's vital signs, things like respiration, pulse, and so forth. And again, there's another YouTube video you want to take a look at. So some of us who are old enough recall the infamous "I've fallen, I can't get back up" commercial from years ago. It's back on TV. There's a link to the retro junk, they call it, commercial. That is back from Life Alert and others like ADT. Again, the medical alert thing, if you have some type of medical emergency, you notify somebody wirelessly. Accelerometers, like those using airbags or the Y game controller, can be used to detect falls. There's other enabling technologies. We mentioned hands, wireless home area networks, RFID 2.0, and biosensors, all for e-healthcare applications. What about transportation safety and autonomous vehicles? Recent TV commercials show automobiles that can stop themselves before crashing. Right now we call that automatic emergency braking, or AEB. It's an ADAS application, driver assistance. It looks like the future holds the promise of an automobile that morphs into a vehicular robot that can be asked to go from place to place under the direction of a passenger and get the passenger to their destination safely. You know, if you consider the number of yearly deaths caused by automobile accidents, this goal seems to be a very noble goal indeed. Most people don't know. Basically, every year, several million people die in car-related accidents. That's an amazing number. In the United States, it's like 40,000. If you take the whole world into account, it's millions. The next smart grid could be the nation's interstate highway system. The Department of Transportation is moving the nation towards an intelligent transportation system called ITS for the nation's highways using ad hoc wireless sensor technology. Call this Communications for Safety, uses V2V or V2R or V2I for safety. We talked about V2V as vehicle to vehicle, V2R is vehicle to roadside, and V2I is vehicle to infrastructure. There's a wireless network, also known as VanNet, Vehicular Ad Hoc Networks, or the IEEE 802.11p network standard, known as WAVE, Wireless Access in Vehicle Environment. I did mention earlier that that's been around for 20 years, and whether it ever gets used is another story. The reason for that is that there's another technology. There's wireless data transmission on the 5.9 gigahertz DSRC, or Dedicated Short Range Communications band, from the side of the road. The FCC has allocated frequencies for that. That's been around for a long time. Whether we use it or not is another story. There's several field tests underway. In Germany, we have the SIM. USA, we have the Michigan DOT testbed, or MCity. There's certainly practical problems with autonomous vehicles: cost, security, location, accuracy, and lawyers. I don't know how many commercials I see of Morgan and Morgan on TV. So I don't know what they'll do if there's not a bunch of highway accidents. Implementation of all this stuff this decade, the 2020s, certainly not the early 2020s, but as we go through the 2020s. There's a link here to the U.S. Department of Transportation you might want to look at. Excuse me. So the major application here is increased safety on our highways. Vehicles could set up ad hoc wireless networks and relay various safety signals or warnings. That is braking, lane change, collision avoidance, radar info, stuff like that. Much sensor-enabled safety technology already exists in today's vehicles. We have airbags, we have ESC, which is electronic stability control, TPS, tire pressure sensors, and I did mention the AEB, which a lot of the 2021 models and the 2022 models, supposedly more of them, will have automatic emergency braking. Here's a graphic figure, shows typical scenario of vehicles talk to other vehicles and local infrastructure. We call that V2X, vehicle to everything, to facilitate traffic flow and promote safety. And there's a link down here, www.car2car.org, where you might want to take a look at that. So there's many YouTube videos that show demos of the emergency braking system, the automatic emergency braking system. You might want to take a look at this guy here, this link to YouTube. Many feel we've entered the era of Transportation 2.0. It's a paradigm shift in transportation, the electrification of automobiles, ships, rail, and many aircraft systems. Today, a typical automobile electronics is run by millions of lines of software code. So in summary, the convergence. The present convergence of technologies will surely affect how humankind will live, work, play, and age. This development is known as the Internet of Things, or IoT, and applications using the Internet for control are known as cyber-physical systems, as long as they are real-time control systems. In the popular press, examples of cyber-physical system applications of the IoT have more familiar names: smart grid, machine to machine, RAM-DEM, excuse me, vehicle to vehicle, V2V, e-healthcare, and infrastructure health are among the more well-known terms used to describe particular applications of this technology. Again, through the use of networked embedded controllers, known as ambient intelligence, and complex sensors and actuators, we call those sensor networks, the goal is to create intelligent or smart infrastructure systems, or CPSs. What's the ultimate purpose of applications of the Internet of Things? To enhance the efficiency, safety, reliability, and security of human endeavors. If you think about it, just about any application can be enhanced by the addition of a monitoring embedded intelligence and the ability to access this embedded intelligence to alter or change the application's operation. Summary of wireless and IoT and CPSs. The newest and most widespread life-altering applications of the IoT, such as smart grid, V2V, and e-healthcare, depend greatly upon wireless internet connectivity. Alternative energy sources are enabled by the smart grid. V2V safety traffic safety applications depend upon ad hoc wireless networks and complex sensors and actuators within vehicles. And e-healthcare requires the monitoring of humans through wireless networks. So wireless will go hand in hand with these new Internet of Things applications.